Generally speaking, fusion is a reaction between two atoms which fuse together to form a larger and heavier atom, as well as neutrons and energy. As far as scientists know, fusion only occurs naturally inside of stars such as the Sun. Fusion occurs by having particles heat up to millions of degrees Kelvin. This insanely high temperature causes the electrons of the atom to be stripped away, resulting in positively charged ions and negatively charged electrons floating around freely, forming a plasma. Since the ions are positively charged, they repel when they are near one another. This repulsive force of charges, known as the Coulomb force, needs to be overcome for fusion to occur. The amount of kinetic energy needed for the ions to get close enough to fuse is called the Coulomb barrier. The strong force is the force which binds the protons to the neutrons and only becomes active once this barrier is passed. There are two factors which strongly contribute to this event, which is temperature and pressure. The kinetic energy of the ions increases proportionally to temperature, and as the pressure increases, a collision is more likely to occur between the ions. Once two ions collide with enough kinetic energy, fusion occurs, resulting in a heavier atom and free neutrons. These free neutrons and atoms' combination of masses is less than the combined mass of the original ions which fused together. This phenomena is described by Einstein's most famous equation, E equals mc squared, showing how energy and mass can be interchanged. In fusion reactions, the loss of mass in the resulting heavier atom and free neutrons has been converted to energy. Fusion is most likely to occur with atoms lighter than iron-56, where the reaction is exothermic. Any atoms heavier than iron-56 result in endothermic reactions, which require an external source of energy, which is why atoms lighter than iron-56 are more likely to fuse and atoms heavier are more likely to split. The most common fusion reaction is between deuterium and tritium, which are both isotopes of hydrogen.
All stars are made up of mostly hydrogen and helium. A star's core burns at approximately 15.6 million Kelvin and is 10 times more dense than lead. At this density, one may question why a star's core isn't solid. Instead, it's made up of a plasma because of the insanely high temperature. The Sun, being 99.8% of the mass in our solar system, is an ideal environment for fusion to occur. Stars have an ample amount of hydrogen, and with their strong gravitational fields, they create immense pressure. This great pressure contains the plasma at the star's core, and the high temperature causes the nuclei at the core to fuse. Every second, the Sun fuses 700 billion tons of hydrogen to produce 695 billion tons of helium. The remaining 5 billion tons has been converted to energy, equivalent to 80 billion 50 megaton nuclear bombs. That's enough nuclear bombs to bombard the entire surface of the Earth over 600,000 times a second.
The tokamak design has three key parameters which will result in producing more energy than the amount of energy put in. These parameters include the temperature of the plasma, the density of the atoms, and the energy confinement time, meaning if the heat is turned off, how long does it take the plasma to cool down? Issues involving inertial confinement include the delivery of the energy to the fuel, symmetrically exploding the outer layer of the fuel, and having the fuel compress evenly. The energy required to heat the plasma is proportional to the density of the ions n, and the rate of fusion is proportional to n squared. If tau is the confinement time, the output of energy is proportional to n squared times tau. If the output energy is to become greater than the input energy, we must have C1 times n squared times tau is greater than C2 times n, where C1 and C2 are constants. N times tau must be greater than 10 to the power of 20 seconds times particles over meters cubed. If Lawson's criterion is met, then the reactor will just break even in the amount of energy output compared to the input energy. For reactors to be practical, the output energy must become much greater.
When nuclear fusion is finally achieved, the world can expect limitless power with abundant fuel. That means humanity can look forward to a power supply to last generations. However, fuel is not so abundant. Fusion requires equal parts deuterium and tritium to work, and while deuterium exists at 155.76 parts per million in our oceans, it can simply be extracted from seawater. Obtaining tritium is much harder. Tritium is exceedingly rare to find on Earth, with only about 20 kilograms of it in existence, most of it being found in the world's nuclear warheads. With tritium being so rare and expensive, leading scientists have proposed using helium-3, an isotope of helium with only one neutron. While it's also hard to find on Earth, the surface of the Moon is covered in it. Without the protective atmosphere of Earth, the Moon is left to be bombarded by solar winds, which carry atoms of helium-3 through the vacuum of space until they collide with the Moon's surface. It has been theorized that it might be easier to mine this helium rather than synthesize it in lab. Helium-3 has the upside that when it fuses, the surrounding materials don't become irradiated. However, it needs higher temperatures to achieve it.
Fusion is a reaction where two nuclei fuse into a single nucleus and a neutron that together weigh less than the sum of the two reactants. This missing mass has been converted to energy, related by Einstein's equation E equals mc squared. The fusion reaction that occurs in stars that scientists try to replicate on Earth is reacting two hydrogen isotopes, deuterium and tritium, to produce helium and 17.6 MeV. Scientists use two different methods to produce nuclear fusion. The first is with magnetic confinement, and the other is with inertial confinement. Magnetic confinement works by manipulating the positive and negative charges which make up the plasma. Inertial confinement uses the inertia of the fuel pushed inward to confine the plasma. A fuel source that can be retrieved from the ocean water, with very little pollution and a large possible output of energy, fusion is an idyllic energy source, but still has not become efficient enough to be cost-effective compared to other sources of energy. The difficulty in producing fusion leads many scientists to say that fusion will not be a reliable source of energy for many decades to come.